All right, this is podcast 4.7 for AP Chemistry, and we're going to talk about the molecular orbital theory. So the first thing we're going to do is remind you on what the localized electron model was. That's what we covered when we were doing hybridization. That model is great for interpreting structure and bonding of molecules. So when we talked about how they would look once they were bonded, when we talked about bond angles or their hybridization, this model works well for that. Some problems, though, that it has is it assumes electrons are localized. That means they stay around the atom that they are from. It deals not with molecules containing unpaired electrons, and it gives no direct information about bond energies. So there is actually a better model that we can use. It's called the molecular orbital model. And in the molecular orbital model, which we'll abbreviate MO sometimes, it deals with covalent bonding still, and what it says is that atomic orbitals of the individual atoms combine and form orbitals that encompass the entire molecule. So those atomic orbitals that are surrounding each of the atoms within a molecule, once those molecules are formed, they become what we call molecular orbitals. So the atomic orbitals are gone and they're reshaped into molecular orbitals. The molecular orbitals that they form have definite shapes and energies associated with them. When two atomic orbitals are added, two molecular orbitals are formed, one bonding and one antibonding. So the example that you see here is if we were to take hydrogen, so these are hydrogen's atomic orbitals, and we know hydrogen has one electron in the 1s orbital. So we take two hydrogens and we add them together. What actually forms is we get a bonding molecular orbital and we get an anti-bonding molecular orbital. The bonding molecular orbital has the electrons between the two nuclei of whatever is bonding. So in this one, with the bonding orbital, you would see the electrons between the two nuclei. With the anti-bonding molecular orbital, there's actually a node here. So what you see are the electrons out here and out here. And we know that that would be a higher energy state because the electrons do not want to be on those sides of the nuclei. They would want to be in the middle. So we have the bonding and we have the anti-bonding. And then how they denote that is this is called sigma 1s, and we know that the sigma bonds exist between the nucleus of the two atoms. And then we have sigma star, and sigma star, anytime you see that star there, tells you it's the anti-bonding orbital. So from the 1s's combining together, you get two molecular orbitals. You get the bonding and the anti-bonding. In the molecular orbital model, the atomic orbitals are added together to form the molecular orbitals, and that's what we just looked at in that picture. Then the electrons are added to the molecular orbitals, following the rules that we've used before. So when we were talking about how electrons fill the 1s and then the 2s and then the 2p, they go the lowest energy to the highest energy, and then there's a maximum of 2 electrons per orbital still, and we want to half fill orbitals of equal energy before pairing electrons. The example that goes along with that, if you remember like the p orbitals where there were 3, we would fill each box first, then we would go back and pair them. So in this one, if we see, for example, 2 orbitals that have the same energy, we're going to put 1 in each orbital first, and then we'll go back and pair them up. So same rules we used before. In the molecule, only the molecular orbitals are available for occupation by electrons. And then the example is the 1s atomic orbitals of hydrogen are gone because the new hydrogen molecule has its own set of new orbitals. So once it becomes a molecule, those atomic orbitals are gone. They're reshaped into these molecular orbitals. The molecular orbital model produces electron distributions and energies that agree with our basic ideas of bonding. So this allows for everything that we know about bonding. It works with all those ideas that we have. And then the labels on molecular orbitals indicate their symmetry, the parent atomic orbitals, and whether they are bonding or antibonding. So what you're going to see here is an example of how we would label these things and how you need to think of it. So this is the 2s and the 2p. Of course, there's also the 1s, but we usually just focus on the valence electrons because everything else kind of cancels itself out. So in this one, we'd be looking at an element that falls in the second row of the periodic table. So say, for example, we wanted to look at fluorine. and we wanted to do diatomic fluorine because we're talking about things bonding here. So with the fluorine, if we want to think valence electrons, it would be 1s2, 2s2, and then 2p6. So that's how we get, not 2p6, whoops, 2p5. There we go. That's how you need to start off first, is just by thinking about the electron configuration. So we know in the 2s, each fluorine, so this is like fluorine 1 and this is fluorine 2. Each fluorine is going to give 2 electrons in the 2s. So those 2 electrons came from that fluorine. Those 2 electrons came from this fluorine. They're also going to give you 5 in the 2p. So there's those, 1, 2, 3, 4, and 5. And there's those. So you fill in the atomic orbital electrons first like this, and then what you're going to do is you're going to move these into the center. So we have 2, 4, 6, 7, 2, 4, 6, 7, and then another 7 would be 14 electrons. So what I'm going to do is I'm just going to fill from bottom to top. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Whoops, I should have gone 11, 12, 13, 14, back and forth like that. But you can see how we pull all of these electrons in and then they all get filled in the middle from the bottom to the top. Now I'm going to clear this so that we can look at what these symbols are. So we have the 2s and the 2p, those are familiar, we've used those before. So this side is for one of the atoms, this side is for the other atoms. And for us, we usually stick with diatomics, so we're going to deal with O2, F2, H2, and they're always going to be identical atoms. You can do this with things that are not identical, but the ones that you deal with, for the most part, are going to be the same atoms just bonded together. So we can see this is sigma 2s and sigma 2s star. So sigma star 2s for your s's here. The s has 1 orbital, so it formed 2, the bonding and the anti-bonding. The 2 p's have 3 orbitals, so you can see that they formed 6 molecular orbitals. We have the sigma, which will always go first, and then we have the 2 pi's. So if you kind of remember, the sigma goes first and then the 2 pi's after that, and these are all bonding. And then after that we have the pi that are anti-bonding, and then at the top is the sigma star. So sigma 2p, and then the pi, and then the 2 anti-bonding pi's, and then the sigma star for the 2p up top. The molecular orbital model can be used to explain why some molecules don't exist. The example we're going to use is, why don't we see diatomic helium? And what we would find out, and I'll fill in the energy diagram for you in a second, is that the total energy of the diatomic helium molecule would essentially be the same as the pair of isolated helium atoms. So there's no benefit for helium to become diatomic because the amount of energy stays the same. And we know that things bond because it's for a lower energy. So if the energy is not going to change, it's not going to happen. So if we look at this, what we would have, this would be your first helium, this would be your other helium. We know heliums have 2 electrons. So we have 4 total electrons to put into our structure here. And so we would put 2 into the sigma, into the bonding box, and we would put 2 into the sigma star. Those just cancel each other out, so the amount of energy stays the same. So that's why you don't see diatomic helium, because these just cancel each other out. There's no energy benefit for them to bond together. When we're trying to figure out if things will bond or not, we like to look at bond order. And bond order is where we do this little calculation right here. We want to take the number of bonding electrons, so your sigma and your pi's, and we want to subtract the number of anti-bonding, so your sigma stars and your pi stars, and then we divide by 2. So the larger the bond order means the greater the bond strength. and you can associate your bond order also with the type of bond. So bond orders of 1 are a single bond, a bond order of 2 is a double, and a bond order of 3 is a triple. We would also know that a bond order of 1 would be the longest, to a bond order of 3, which is a triple bond, is the shortest. And the shorter it is, the more strength it has. Okay, and we have two examples for how we calculate bond order here. So for diatomic oxygen, the first thing we need to figure out is the electron configuration for an O, for an oxygen. So an oxygen would be 1s2, 2s2, and then 2p4. So we're going to ignore the 1s. We're going to look only at valence electrons because remember those will cancel each other out. So we have 2 electrons in the 2s, so we'd put 2 there. And then in the 2p there are 4, so we'd go 1, 2, 3, and then 4. And we know that's going to look identical to the other side because we're bonding 2 of the same thing together. So I'm going to go ahead and fill that in. So this is for our first oxygen, and this is for our second oxygen. So we're going to take these electrons and we're going to fill from bottom to top. So I'm going to count these up. We have 2, 4, 6, 8, 10, 12. I have 12 total electrons I have to fill in. So I would go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that's filling in my molecular orbitals. Then the next thing I want to do is calculate my bond order. So I want to take all my bonding electrons, so anything that does not have a star, so it'll be 2, 4, 6, 8. So I have 8 bonding electrons. I want to subtract the antibonding. So there's 1, 2, 3, 4. And I want to divide by 2. So 8 minus 4 is 4, divide by 2 is 2. And that should make sense because we know if we were to draw the Lewis structure for oxygen, it would come up with a double bond that we would need. So oxygen has a bond order of 2, and we can see that and how we calculated it here. So let's do nitrogen. Nitrogen's electron configuration is 1s2, 2s2, 2p, 3. It has 1 less electron than oxygen. So to fill these in, we have 2s2, again ignoring the 1s, and then in the 2p's we only have 3, so 1 in each box. This side will be identical because we're bonding 2 nitrogens together. So in this case I have 3 plus 3 is 6, 8, and 10 electrons. So 10 electrons total is what I need to fill in. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that's what my molecular orbitals would look like once they're filled. Then to calculate the bond order, I take my bonding, which is 2, 4, 6, 8, minus my anti-bonding, which is only these 2 right here, and divide by 2. So 8 minus 2 is 6, divide by 2 is 3. And that makes sense because we know when we draw nitrogen, we see a triple bond in the middle. So that's how these work. Okay, the homonuclear diatomic molecules, that's what we were talking about, how we'll do a lot of H2s, O2s, F2s, same atoms, 2 of them stuck together. Only the valence orbitals of the atoms contribute significantly to the molecular orbitals. That's why we were not focusing on like the 1s. We were only looking at the 2s and the 2p's in the example that we did. Paramagnetism and diamagnetism are 2 vocab words that you need to know. Paramagnetism is a substance that's attracted to a magnetic field, and an example of that is oxygen. And if you look back to the very beginning of this video, there's a picture on the first slide. That picture is of liquid oxygen being poured through a magnet, and you can see that it's actually attracted. It gets stuck in between the 2 magnets. And the reason that is electrons are unpaired in oxygen. Those unpaired electrons make it attracted to a magnetic field. The nitrogen that we did had paired electrons, so everything was paired up. It was really nice and clean, and that's called diamagnetism. That means it's repelled by a magnetic field, it's not attracted. So dia, you're just going to have to think 2. Unpaired for paramagnetism. These can be a little tricky to remember what goes with what, but these are like your oxygens, so they are attracted to a magnet, and these are not attracted. And on this slide right here, you can see some second row diatomic molecules, and we can, what they've done is they've filled in the molecular orbitals for us, and we can look. And so, for example, we can see that boron, the diatomic boron, has unpaired electrons right here. There's one on this 2p orbital and one on this 2p orbital. So it's paramagnetic. It would be attracted to a magnet. This carbon would not be, C2. N2 would not be. O2 is. We have those 2 unpaired electrons right there. Fluorine is not. It's not attracted. So that's all that information right there. It also gives you the bond orders if we were to calculate them, and then observed energies. And you can tell by the bond length, where we also talked that the higher the bond order, the lower the bond length, the shorter it is. You can see that right here. We know nitrogen, when we calculate it, had a bond order of 3, and it has the shorter bond length of these. So longest is a bond order of 1, and then it gets shorter and shorter. So this is actually a really nice picture. It's also in your book. You can go to look at it. It gives you a lot of information. But that's it. So kind of understanding the idea of molecular orbitals and how when these things combine, they go from atomic orbitals and then they kind of morph into these molecular orbitals that are for the whole molecule. And then we'll talk more about this in class.